Today we're going to be talking about transcendent memory. Some of you may have seen a previous presentation on transcendent memory. Actually, why don't I ask that? Please raise your hand if you've seen a previous presentation on transcendent memory. Okay, roughly a quarter. The first, I wasn't quite sure how to handle this because it's a very deep topic and there is a great deal of progress that I wanted to cover, but I also didn't want to bore the people that have never seen anything before. So what I'm going to do is spend the first few minutes and maybe about 10 minutes of the time doing a very quick overview of what transcendent memory is. And those of you who have seen it before, I guess you can consider it a review or take a nap. I will make sure I point out when I'm starting to cover the new material, so then you can pay attention. So what I'm going to do is talk about what this problem is that we're trying to solve, and then do this brief overview of both how physical memory is managed in a real bare metal operating system and then in a virtual environment. Talk a little bit about TMEM at a high level, and then we'll switch over to the new material, progress on TMEM since the last Zen Summit North America 14 months ago. And then I've got some very interesting performance analysis that I've been doing, and hopefully we'll have some time left for Q&A. But I don't want to steal from George's time, and I know everybody's on a tight schedule, so I'll try to rush through this. If you really are interested and want more information, I'd be happy to talk to you either afterwards or even talk to you on the phone sometime in the future. Okay, so many Zen users have consolidated their data centers, and they find that their CPUs are still spending a lot of their time idle. And this is because the real bottleneck is that there isn't enough RAM in the system. One solution is to go ahead and add more memory to all the systems, but if you've got a lot of systems or need to add a lot of RAM, that can be very expensive. And wouldn't it be nice if we first ensure that the memory we do have is being used efficiently and not just wasted? Unfortunately, it's not often easy to recognize the symptoms of inefficiently utilized memory, even in a bare metal OS, let alone in a virtual environment. So before we try to solve the memory problem, let's try to clearly identify what the problem is, what we're trying to do. Our objective, which is deceptively simple, is to make as good as possible across time, meaning not just once, but continually while the machine is running, how RAM is distributed among a set of virtual machines. And we not only want a set of virtual machines, but we want a maximal set, as large as possible. And we're going to do that by measuring how much RAM each virtual machine needs now and how much it needs in the future. We're going to take memory away from those VMs that don't need as much and either give it to ones that need more or use it to provision additional VMs. And we want to do all of that without suffering any kind of significant performance penalty. So to do that, we're going to have to first take a look, do a quick overview of how physical memory is managed in an operating system and in Zen. And the first thing to note is that operating systems are memory hogs. And why? Well, most OSs were developed many years ago when memory was scarce and precious, and every bit of it had to be put to good use for something. So as a result, if you give an OS more memory, it's essentially going to grow fat and use up whatever memory you give it. So it's really not very easy to tell if an OS needs more memory or not, and it's not very easy to tell whether it's using the memory that it does have efficiently or not. So let's dig a little deeper now and see how an OS is using memory. Well, an OS has some memory for a kernel and some for users, and there's a thing called a page cache. What's a page cache? Well, most OSs use a lot of RAM for that page cache, and because disks are slow, an OS is often going to keep copies of pages that it has already read from the disk, so it doesn't have to read them all over again if it needs them again. The OS is essentially trying to predict the future, so it makes disk reads less frequent. And it's going to store those pages in something called a page cache. And although an OS is far from perfect at predicting the future, it guesses right a lot of the time, which is why the page cache concept exists in just about every modern operating system. If an OS attempts to predict the future and guesses right, we're going to call that a good page cache page, and we're going to represent it with this crystal ball. Okay? So I said the OS guesses right a lot of the times, and that means it also guesses the future wrong a lot of the time. So that means that a lot of the pages in the page cache are pages that are really not going to be used in the future. It doesn't know that, but they're not going to be used, and that valuable memory space is actually being wasted. We're going to represent that with this toxic waste symbol. If you watch over time how memory is being used, and I could do a fancy graph here, but you can imagine it in your mind, how memory is being used. When an OS is really busy, the page cache gets shrunk down because all that memory is being used for real applications. But when the operating system is less busy, all that memory is instead transformed into page cache pages. So let's see, when the workload is light, then if you have all this page cache pages, a lot of those pages may be useful, but much of the time, most of the page cache is containing things which might be useful in the future and maybe not, but some, maybe most, maybe even all of it is going to be wasted. Okay, so now we're going to switch back to Zen. When Zen reserves some of its memory, and by the way, am I going too fast? For those of you who haven't seen this before, I'm trying to go very quickly, but let me know if you have a question or if I'm skipping over something way too quickly. So Zen reserves some of its memory for itself in the upper right corner there, and lower right corner it reserves some memory for domain 0, which is a special pig, but still a pig. And Zen partitions the rest of memory for some guests, to launch some guests, and anything that's not left lying around is kind of sitting there waiting for more guests to launch. But unless you're really adding up the megabytes that you're applying to all your guests and trying to use up every megabyte in the system, there's almost always some left lying around. And we're going to call that fallow memory. And that fallow memory is really completely unused. It's completely wasted. Well, there are times when you want to have fallow memory, like when you're migrating. Migrating is one of the coolest features of virtualization, but one of its constraints is unfortunately that every migrating VM needs its whole physical memory allocation, both on the source machine and the target machine, for a short time. So it's actually using, for a short time, double its physical memory allocation. And if you don't have fallow memory lying around in the system, on different systems at all times, migration may not work at all, or at least it's going to be very limited. Another widely used technique for managing memory in a virtual environment is called ballooning. A balloon driver essentially allows the hypervisor to redistribute physical memory from one guest to another, but it has some real issues. One is that it works really great when you have fallow memory that you want to assign to a guest OS. But for several reasons, ballooning doesn't work so great the other way around. You can't just take memory away from a guest with ballooning. You have to essentially ask for it to give it up. You often won't get it fast. Sometimes you won't get it at all. This is because, as we saw earlier, every OS really thinks that it's using all of its memory for something useful. It doesn't want to throw it away. Second, when the balloon driver wants some of the memory, the hypervisor has to take it away from another virtual machine, and that OS in that virtual machine has to decide what memory it needs the least. And that's going to be page cache pages. And as we've seen, while some of those page cache pages are really wasted, okay to throw away, some of them are actually valuable, and throwing them away is going to result in extra disk reads. Third and worst, ballooning decisions have to be made external to all the guests, which means they have to be made by Zen or domain 0. And those two have very little guidance as to how much memory a guest needs and how much is safe to balloon and how fast it can be taken away. And if it guesses wrong, bad things can happen, like running out of memory. Things get worse if you combine ballooning and migration. Suppose you try to do this ballooning thing and you do your best to dynamically distribute memory, but because all guests are memory hogs, they're all trying to get everything they can, there's probably not enough fallow memory lying around so that when an incoming migration wants to land on this machine, that there's memory available. So it's a problem. So this problem that we're trying to solve, that I showed earlier, we've got a pretty good list of reasons why it is a hard problem. OSs are memory hogs, Zen leaves memory fallow, ballooning helps, but it has some problems of its own. So it should be fairly obvious that the situation that we have today for managing physical memory isn't really working. And so we need to do something new. And that leads us to transcendent memory. So I'm going to do a very quick overview of transcendent memory. Many of you have seen some of these slides twice, or maybe more. What we're going to try to do with Transcendent Memory is surprisingly simple, and this is kind of an overview. Step one, we're going to reclaim all the wasted memory in the system from the hypervisor, that fallow memory, and from the guests. And we're going to collect it all into one big pool. And step two, we're going to provide indirect access to that pool of memory through a carefully crafted API. And that API is controlled by a set of restrictions that are imposed by the hypervisor. And that's it. But the magic is in the characteristics of that API and in the semantics of the restrictions that are imposed by the hypervisor. First, that API does require awareness by the OS. It requires changes. It's impossible to do this without any change to the operating system or doing it in a module. So it requires a few lines of change. It's surprisingly small, but the changes are required. The API that is specified has been carefully designed to be narrow, requires a small set of hooks in Linux, and it funnels down to a single Zen hypercall. We have a spec online today, and TMEM works primarily by synchronously copying whole pages between the guest and the hypervisor back and forth. We're doing a lot of things with this already. I'll talk about one or two of them, but because we think there's a lot of potential here, we want to make sure it's extensible, so the API is extensible in case we find more uses. So last slide on Transcendent Memory as a whole. Transcendent Memory, which is that huge pool of memory we saw before, can be dynamically subdivided into subpools, and when those subpools are created, they have certain attributes. Ephemeral is a key attribute. It means that any data that's put into the pool may disappear at any time. So the hypervisor has complete flexibility over whether the data in the pool stays around long enough so that it can be used if the guest needs it again. Or, for example, if the space is needed for an incoming migration, all of the data can be immediately thrown away and reused to house the incoming migrating virtual machine. Persistent means the opposite. Any data put in a persistent pool is going to stay there, but only as long as the guest is surviving. So it's not really like a disk is persistent. It's just living there as long as the guest might need it. There's private and shared, but I'm going to skip those because we're trying to rush through this part of the presentation. Okay, so we're back to the agenda now, and if this is the new material, so if any of you are napping or have gone outside, or in fact, if you see that your neighbor is napping, if you could tap them on the shoulder now, I'd appreciate it. As of earlier this month, when 4.0.0 released, TMEM released along with it. It was announced in a number of places in the trade rags. And actually, not many of them got right exactly what it was, but it's kind of complex, so that's okay. It has to be enabled within Zen in 4.0 with a boot option. Second, we put a lot of effort into the locking strategy so that TMEM provides a really high level of concurrency so that not only can multiple guests access TMEM simultaneously, but different vCPUs within a guest can access it simultaneously. In essence, it's the number of physical CPUs in the system can all access it simultaneously if it needed to. There are some interesting challenges in that, and I'd love to talk to you about it, but I can't do that in the short period of time. TMEM has complete save and restore support now. It has live migration support, and that's in the hypervisor and in ZenD. And it's not in libxl yet, so I'm going to be working on that next. A new feature just added post 4.0, but is now in 4.1 and 4.0.1, is called page deduplication, and I'll talk about that more in a minute. The Linux kernel patch recently was reposted and is getting discussion in the LKML mailing list. And the new patch has support for all the most important file systems, as well as some nice sysfs interface so that within the guest, you can actually see what's going on and measure it and get some statistics. And TMEM is starting to find its way into different Zen and Linux distributions, including Oracle VM, which is Oracle's Zen-based virtualization solution. So what is this page deduplication stuff? It's in Zen Unstable, like I said. It's been backported now, I think, thanks Kier for putting it in 4.01. And it's enabled with yet another boot option. And if you've heard of page sharing, it's a lot like that. If you've got 50 pages that have been put into TMEM and their contents are all identical, instead of taking up 50 pages of real physical memory, instead, We just keep one copy in physical memory and use 50 pointers to it. It is completely transparent to the guests. If they have TMM turned on, and this option is turned on in Zen, all of them will just automatically take advantage of it. It's fairly simple, and it also differs dramatically from the page sharing that was described, the other page sharing that's in 4.0, and from KSM in Linux and that other virtualization system that starts with K, I heard it called. In some ways, it's a lot easier because for ephemeral memory, for example, all the difficulties of copy on write that are necessary with shared memory, with page sharing, are not necessary, and we don't have to do any swapping. So it's really a lot easier, and adding dedupe support to TMEM was less than 500 lines of code. Dedupe is currently restricted to just ephemeral pages for some fairly subtle reasons, which we can't get into now. It can be combined with compression to get, as we'll see, some pretty impressive results. And we've been experimenting with something that I call trailing zero elimination, which is kind of a poor man's compression when there's a workload which has a lot of small files, because those files tend to be zero filled. And if you got a lot of files that have 100 bytes in them, the rest of them is zero. We don't need to compress because we can just kind of represent the other zeros somehow and store the 100 bytes that are relevant. Last, there's a good set of statistics that TMEM provides through the XM interface, and dedupe adds some more so that you can really see what's going on, how many duplicate pages are being shared, how much time is being taken, and that's all really useful stuff. So, as they say, every silver lining has a cloud, and for TMEM there's a fragmentation issue that it was actually Jan Bulik that discovered this shortly before 4.0 went out. And basically the problem is that there's a few Zen operations that require internal data structures that have to be dynamically allocated and that are larger than one page. And if the multi-page data structure allocation fails, then the operation fails also. Well, any dynamic memory technique, including just ballooning, is going to eventually churn through all the physical memory in the system and fragment it, so that multi-page allocations will eventually fail. TMEM just does this very quickly, and Jan Bulik ran into it, and especially when it's tied to aggressive ballooning, which we'll talk about in a minute. So under certain circumstances, we had these issues, and we found a kind of a hacky workaround, got it into 4.0. It seems to be holding pretty solid, but the real problem is this fragmentation issue in Zen, and it really needs to be fixed at some point. That's the real answer, not this hacky workaround. Okay, so we're going to talk some performance analysis now, and then if we have time, any questions. So here's a test workload. We've got a 2-core processor. Well, actually, first let me pause here before we get into the test stuff. Are there any questions? Is this going way too fast? Any obvious questions that I've missed? Okay. The test workload here is a system that I have at home, a dual-core Conroe, has 2 gig of RAM in the system and just has standard IDE disk. What I'm going to do is put 4 single vCPU para-virtualized VMs on it, and each one has 384 megabytes of memory. That's so it'll fit in the 2 gig of RAM. And we're going to pound on all of them. All of these VMs are simultaneously running a parallel kernel compile workload. Okay, so we're going to run that workload 5 times for each of several configurations. We're going to collect information using like ZenTop and the XMTMEM output tool, and we're going to take down a few important statistics. And we're going to measure this on 5 different configurations that are shown there. Now, 4 of these 5 configurations include something called self-ballooning, and so I'm going to digress for a minute to talk about that. Self-ballooning was presented at Zen Summit 2008 in Boston, and it's essentially a feedback-directed ballooning technique which takes information from within the guest OS to dynamically resize the balloon. It gives away physical memory when the guest OS doesn't need it and asks for it back when the guest OS has a workload that does need it. This is done very aggressively so that a guest OS uses as little memory as it can at any time. It's done frequently so that if there's a sudden change in workload, that it can try to respond to it. It's done independently of other guest OSs, so it doesn't have to go through some central feedback mechanism. And it has a lot of parameters so we can configure it over time as we experiment and learn more about it. On Linux, there's a variable called committed AS in proc meminfo. And what it is a reasonable guesstimate of how much memory is being needed by the operating system. And Red Hat, in one of the Red Hat documents, I found this, which describes it. It's essentially how much memory the machine needs right now, and we use that to feedback and drive the balloon driver off of it. And in Zen Summit 2008, this was done with a user land daemon. And the source, since I'm making changes for TMEM in the kernel anyway, I've made changes to the balloon driver, and so this is driven from inside the kernel now for these tests. So let's see how self-ballooning does just by itself. On this workload, we see a small increase in wall clock time, and I guess I should explain the terminology here. The line on the left with the arrow in the middle, that's a range. The lowest value, the highest value measured, and the average of the middle three. That's what this represents for all of these. You might have seen on the mailing list I was running some problems with the scheduler. I was getting a kind of a wide variation in results, so I decided I'd represent it this way. It's not so wide that the results are statistically meaningless, I don't think. Tell me otherwise if you're a statistician and you see some problems. So wall clock time goes up, total vCPU time goes up. And by the way, total vCPU time is the sum as measured by XenTop of the vCPU seconds of all 4 VMs plus domain 0. Okay? Whereas wall clock time is from the time the workload starts to the time the last compile is over, and I actually crashed the virtual machines at the end, so I'm sure that they're not using any extra cycles. And then domain 0 recognizes when the last one is crashed and stops as well. So these should be fairly accurate numbers. So on virtual block device, we'll look at reads and writes in millions of sectors. And you can see here that the number of reads has gone up by about 10%, and the number of writes is about the same. And so there's a performance hit from self-ballooning, right? And why not? Well, we would kind of expect that. Because what we're seeing is all those good page cache pages from earlier in the presentation, all those good page cache pages are not there anymore, so the disk has to be used again to go refetch those off of the disk. And because we squeezed all those pages out of memory with self-ballooning, we have to go get them again, and that causes the number of disk reads to go up. And this workload doesn't really show it because this load, the kernel compile, is relatively constant. But if the guest OS needs memory now, you're going to lose some swapping as well. It has to swap out pages to disk and may even run into an out-of-memory condition. So anyway, this loss of performance with self-ballooning is expected. In fact, if you go back and look at the Zen 2008 paper that I did, this performance degradation can actually get much worse under certain conditions. So, if you think about it, those problems with self-ballooning that cause a loss in performance are exactly those things that I told you that TMEM is good for. So what if we combine the two like that? Instead of copying pages to and from the disk, because of self-ballooning, we're going to be copying pages to and from transcendent memory. And we'll see if that'll help. So let's take a look at the rest of the results. So first, wall clock time. TMEM not only makes up for self-ballooning, but is even faster than the unchanged OS. And when combined with deduplication and compression, then it really rocks. 5 to 8% faster to completion on the left. What about vCPU time? Well, there is a small hit for TMEM by itself, but there's a rather significant hit with deduplication and compression because compression is relatively slow. How important is it that the vCPU time goes up? Well, if you've completely saturated your CPUs, then yes, that could be a problem. If you haven't, which is the case here, even though I've tried very hard to overcommit this system, we'll see. So we'll talk about that more in a second, but let's look at the disk stuff. With TMEM, we see that we not only recover the hit in disk reads due to this fact that we have to go back and get pages all over again, refaults, I guess you could call them, but we reduce it by 31% for TMEM by itself, and it's reduced by over 50% if you have deduplication and compression. And again, no noticeable changes in writes. We're not trying to fix writes. It's just reads we're concentrating on here. So this all looks pretty impressive. Why is it so good? Well, TMEM is basically acting as a big shared page cache, shared across all the guest OSs. And if you know a branch of statistics called queuing theory, you'll understand that this is mathematically better than a set of smaller page caches. Then when you turn on deduplication and compression, the size of the single shared page cache is quadrupled in size, at least for this workload. Any swapping is also sharing that large pool of memory. We're not seeing much of that now, but it could. And so what about that vCPU increase? Well, virtualization was first conceived as a way to more effectively utilize CPU cycles. In this workload, the CPU cycles aren't being used. So TMEM is doing exactly what virtualization is supposed to do. It's not only making better use of the underutilized physical RAM in the system, but it's also making better use of previously underutilized CPU cycles. And remember, with this workload, I'm pounding on all those guests simultaneously. TMEM is really designed for a much broader set of statistical situation where different guests are using memory at different times. So it may even get better if the usage of the machine is more sparse. So to summarize, TMEM's primary objective is to make memory more flexible, a more flexible resource, and to do it better than ballooning and other memory utilization technologies with fewer disadvantages. It certainly works well on this workload by showing both a dramatic reduction in disk reads and a faster time to completion while utilizing the CPU more effectively. Some disadvantages, well, operating system does need to be changed. I'm working on that, upstream Linux. It won't work with Windows unless Microsoft gets in the picture or there's some very smart binary translation that's done. I don't know. It's not impossible. It should work in HVM Linux domains if the patches are applied. I haven't tried that yet. Other disadvantages, since you're using more CPU cycles, well, it's higher power consumption. Maybe that'll make up for, be made up for by doing fewer disk accesses so your disk isn't spinning as much. I don't know. I haven't tried to measure that. There's some trade-offs there, and you can decide whether it's a good answer or not. So before I conclude, Jeremy has done a really hell of a job giving me feedback for some of the TMEM changes on the Linux side, so I wanted to acknowledge him wherever he is. Stepped out, oh well. Thanks, Jeremy. And if you need more information, this is the same web page as a year ago. It's been updated somewhat, a lot of stuff there. I also just submitted into the tree an internals document which describes everything that's going on inside of the implementation of TMEM. And so if you're interested in like making changes or trying things or using this for your research objectives, it should be all fairly easy to understand. And finally, send me email if you have any questions that I can answer directly. And that's it.
Thanks, Dan.
Okay.
Do we have any questions?
Apologize that went so fast, but trying to catch up here. Steve.
So this sounds like fun. You've got one experiment you've done, macroscopic experiment with those 5 kernel nodes or 4 kernel nodes, whatever it was. Do you plan to do some more?
The question is, do I plan to use more? There's the hero. Yes, a lot more performance analysis really does need to be done. There might be some corner cases where, well, there are going to be corner cases. Any caching system can be broken if you know how to do it.
I think in particular, it seems that you're using the same kernels with the same file system and the same
So, yeah, yes, I am using.
the best case scenario for a caching system.
It's the best case for the caching system for when you're trying to do deduplication. And yes, if your workloads are completely different, deduplication is not going to work as well. But TMEM still works regardless of what the workload is. Now, that's not quite true in that I guess I should add that TMEM does not work with a database. And I work for a database company, but the database does its own page caching, and it doesn't use the operating system's page cache. So this is not something that's really cool for Oracle databases yet. We might find some other ways to do this in the future. But there are some architects at Oracle that believe that this is exactly what's needed for some kind of Oracle in a virtual environment. I'd love to have performance experts pound on this, try some different workloads. The worst case should be fairly small, because if you're approaching 100% CPU saturation, it's likely that you're not doing a whole lot of disk reads and writes. And this is all, the advantages are taking away disk reads and writes. If you're doing a lot of disk reads and writes, you're probably not doing as much CPU. And so wasting CPU for compression and things is not that big a deal. So there's an interesting trade-off here, and I expect to not have problems, but it does need more work. Questions?
So here, so are you assuming that the VMs are fundamentally friendly to each other, or if not, how do you ensure fairness?
Good question. It is possible with TMEM for a single VM to cause what's essentially a denial of service attack on the others. If it keeps pounding on TMEM, then the other ones may not be able to use it as much. There is, just like with the CPU scheduler, there's weights that can be applied, so you can ensure that no VM is able to use more of TMEM than its share. That defaults to off, so yes, it assumes that there isn't any maliciousness going on. If there really is one that is using it heavily as part of its normal work and other ones aren't using it heavily, that's fine. That's the whole point of balancing the load. So, but you do want to stop malicious VMs, and I can do that. Any more questions? Delore. I'm sorry, what was that again? Mm-hmm. Right, so we're answering the question again about the possible denial of service. Those features are built into TMEM. I've just got them off by default because I wanted to see, we want to assume that we're trying to maximize the workload across all the systems, but you want to make sure that if one is malicious, you can stop them. So I'm not sure, does that answer your question?
It doesn't particularly need on some page, that's what I mean.
Right. It doesn't really need it. It would be difficult, but not impossible for a malicious OS to try to break it. I'm sorry, was it Luke?
Yeah, I know I talked to you earlier, and I'm also very concerned about the fairness, but
Mm-hmm.
Actually hearing your thing, I think a lot of the things I was worried about, I'm getting confused by you talking about the ballooning it down, and it sounds like TMEM doesn't mess with the user page cache unless you add in the balloon.
Right, the balloon driver.
That was what I was thinking about.
If you're not doing ballooning, if you just have static RAM for all of the virtual machines, then the fallow memory that's left over can be shared among them, but you're not creating any memory pressure. You're not taking any memory away from the VMs.
So in that case, what's my worst case if I got some guy who's going crazy on the TMEM? Is TMEM, what's the worst case?
There is a very small cost for using TMEM. Exactly how to measure that in this kind of worst case analysis, I'm not sure. It should be relatively small because it's only done when pages are evicted from a guest page cache. That's the expensive part. A page is copied. So if you had tens of thousands, hundreds of thousands of pages that were falling off the end of your internal OS page cache, then that would start to get expensive. But that only happens if you're pushing them out with applications or with lots of disk reads, like grepping the disk or something. Could be an interesting corner case, I guess I could measure. Okay. Thank you, everybody. All yours. Oh, you need
Okay.
the mic.